All right, welcome back. In this video, I'm going to be talking to you about systems of equations and also row reduction. And you probably have experience in solving linear systems from other classes, but in this class, we're going to take the same three-step process every time. We are going to write the system as a matrix, row reduce the matrix, and then we'll interpret the solution. But I don't think you know how to do any of those three things yet, so I'm going to show you how to do all three in this video. So let's start with how are we going to take a system of equations and write it as a matrix. And I think the best way is going to be for me to just show you an example. All right, so we're going to have ourselves a system. This is a 3x3 system because it's 3 equations and 3 variables, and we'll see that that generates a 3x3 coefficient matrix. Okay, so the coefficient matrix, what we do is we copy the coefficients. So 1, 2, 1 for 1x1, 2x1, and 1x1 in the 3 respective equations. 2, negative 1, 1, and 1, negative 1, 3. Okay, this is what we would call the coefficient matrix. Now, I'm not going to give you the definition of the coefficient matrix in terms of, like, a system with a1, 1x1 plus a2, 1, 2x2 all the way. Yeah, we don't need to do that. Okay, you can see what I did there. That's going to be the coefficient matrix. But what we're going to mostly do is we're going to take the information provided by the 4, 1, 0 as well. So we will add a little vertical bar, which is really just there for your eye. It doesn't really mean anything. And we'll add it on like that. And this is what we will call the augmented matrix. And this is what we're going to really be working with mostly in this class. Next, we're going to want to produce the matrix, but we don't really know what that means yet. So I need to, give you some definitions and a couple of applicable theorems, and then I'll show you how. So first, I'm going to tell you that we're going to say 2 systems are equivalent if they have the same solution set. Okay, that will be relevant to us. And the elementary row operations that we can do to a matrix are we can swap 2 rows, we can multiply a row by a scalar, and we can add a constant multiple of 1 row to another row. And then we'll say 2 matrices are row equivalent if one can be obtained from the other by a sequence of elementary row operations, which kind of leads us to the theorem that says that row equivalent matrices represent equivalent systems. So what that means is we're going to go to the augmented matrix. We're going to apply elementary row operations to get to a point where we can more easily see the solution space, and then we can say, okay, well, we found the solution for the original. But I would propose that that's actually what you've been doing all along when you've done elimination and even substitution in your previous algebra class. So back to our earlier example, I'm going to want to apply row operations to this matrix to get it down to something that we would call fully reduced in this class. I mean, in the textbook, they're going to call it reduced echelon form, and that's pretty common. But there's slightly different terminology. So I need to tell you about echelon form and reduced echelon form. So I'll tell you a matrix is an echelon form if all the 0 rows are, all 0 rows are at the bottom. The first entry in a given row is always 1. And if row k plus 1 has non-zero entries, its first non-zero entry on that row is to the right of the first non-zero entry in the previous row. Which you might be like, what are you saying here? And we don't care that much about echelon form because what you'll find is that echelon form is like almost fully reduced, but not fully reduced, and we want to fully reduce these things for us to get a good solution. So this is a matrix that's in echelon form, but is not fully reduced, because as you'll see, there's more that we could do, and if you don't see, just kind of come back to this matrix in a minute or so. And maybe I'll just give this a little annotation. Now we'll say that a matrix that's already in echelon form is in reduced echelon form, which we're going to kind of colloquially call fully reduced, if the first non-zero entry in a given row is the only non-zero entry in that column. So let's go back and look at the one that was in echelon form and see how it's not in reduced echelon. All right, it's back. So in order for this thing to be fully reduced, I'd need that 5 to not be. The first non-zero entry in a row is the only non-zero entry in its column. Okay, so that would be like this. Okay, that was okay because it wasn't the first in its row. And then 1, 0. Okay, and also because it's in echelon form, that first non-zero entry is going to have to be a 1. But I think you'll grow to see why we want those ones, those leading ones anyway. So let's go and let's row reduce this thing. So before I begin, I'm going to just tell you that, there is some sort of algorithm that if you follow it every time, you will always get to reduced echelon form. But I also like to, I think that you're just going to want to take your own path. So, like, I'm going to start off with, okay, I need to get a pen. And the first thing I'm going to do is I'm going to use this 1 right there to clear out that 2 and this 1. Okay? And I'm going to do that by taking row 2 minus 2 copies of row 1 and then leaving that in row 2. And then I'm also going to take row 3 and I'm going to subtract 1 copy of row 1 and I'm going to leave that in row 3. Now in this linear algebra class, I'm not going to be super strict with you on like reporting all of your row operations all the time because we just need to get to the point where we're able to row reduce a bunch of matrices, and I'm not going to have time to check everyone's row operations. Just row reducing incorrectly will be its own penalty, right? So, but at the beginning, I'm definitely going to show you what I'm doing. So I'm going to go over here, and I'm going to have 1, 0, and 0. All right, because that was the whole point of subtracting those copies of row 1. Okay, row 2 minus 2 row 1s is going to be -1 minus 4 is -5. Okay, -1 minus 2 more is -3. Okay, I'm not liking the look of this, but it's okay. And grabbed an example from the textbook that they didn't actually reduce, and I'm realizing that may have been a mistake, but it's okay. And 1 minus 2 times 4 is 1 minus 8 is -7. We have not changed the first row. 1, 4. Okay. And then down in the third row, I've taken row 3 and I've subtracted row 1. Okay, so 1 minus 2 is -1. 3 minus 1 is 2. And 0 minus 4 is -4. Okay. Now what I'm going to do is I'm going to use this 1. Okay, this is not a 1 yet, it's a -1, so I'm going to multiply row 3 by -1. Negative row 3, leave that in row 3. So this will become a +1, this will become a -2, and this will become a +4. Now, my next step is I'm going to take this 1 and I'm going to clear out that -5 and this 2. Right? So I'm going to say, because otherwise, if you try to take that -5 and turn it into a 1, you're going to have a 3/5 and a 7/5, and if at all possible, you want to avoid going into the realm of decimals or fractions, or at least put it off as long as possible. Sometimes it's going to be impossible, right? Sometimes your solution is not an integer. And okay, so yeah, I'm taking, whoops, forgot to report what I'm going to do. I'm going to take row 2 and I'm going to add 5 copies of row 3. And then I'm going to take row 1 and I'm going to subtract 2 copies of row 3. Okay, so that's going to be 1, 0, 0 still. Okay, this will become a 0 and so will that. This will stay there. We're not doing anything to row 3 right now. Okay, I'll put that vertical bar there, just give you an idea of what you're looking at. Okay, I took row 2 and I added 5 copies of row 3. So I've got -3, and I'm going to add -10 plus 5 row 3. Okay, and that's -13. Okay, and then I'm going to take -7 and I'm going to add 5 copies of row 3, which is going to be 20. Okay, so if I take negative 7 and I add 20, I'm going to get 13. Oh, okay. See, there you go. And it's going to end up working out just fine. And then over here in row 1, I'm going to be subtracting 2 copies of row 3. Row 1 minus 2 row 3s. Yeah, okay, so 1 plus 4 is 5. And let's see, if I take row 1 and I subtract 2 copies, if I take 4 minus 8, I'll have negative 4. Now I'm going to take row 2 and I'm going to divide it by negative 13. And I'm going to have a 1 and a negative 1. Okay. Then I'm going to use that 1 right here as a tool to get rid of the negative 2 and the 5. And that'll be kind of almost my last steps. I'm going to take row 1 minus 5, row 2. Okay, and I'm going to put that in row 1, but I'm not going to have room to report that. And I'm going to take row 3, and I'm going to add 2 copies of row 2. Okay, so I've got 1, 0, 0. And then I'll have row 1 minus 5 copies of row 2. So negative 4 plus 5 is 1. I have not changed this. And 0, 1, 0. Okay, and I'm adding 2 copies, so 4 minus 2 is 2. Okay, I feel pretty good about that. All right. Now, we're almost done, right? But back in the fine print of the definition of echelon form, it said that basically the first non-zero entry in a given row has to be to the right of non-zero entries in previous rows. So we're going to row swap row. And now I will have a matrix that is in reduced echelon form. Oops, I need a pen. And that's great and all, but I really want to kind of go back to where we started with writing the augmented matrix for the system. Okay, so what just happened here? We just took row operations, elementary row operations, to transform the red matrix to the black matrix to put it in reduced echelon form. Okay, we know that applying elementary row operations preserves the equivalency of the system, right? And if I were to take this out of the matrix form and to write it, in terms of the variables like we did at the very beginning, I'd be saying 1x1 plus 0x2 plus 0x3 equals 1. 0x1 plus 1x2 plus 0x3 equals 2, and 0x1 plus 0x2 plus 0x3 equals negative 1, which is saying that, x1, x2, x3 as a vector is equal to 1, 2, negative 1, and these are the values of x1, x2, x3 that solve my system. Okay, so this is in general how we're going to solve systems in the class. And I completely forgot to change my heading, but that is us interpreting the solution. Okay, I'm going to show you a couple of other situations. I'm going to kind of fast forward through the row reduction because this is something you just need to practice yourself, and talk about other situations that can happen other than us reducing and getting down to one nice clean. So let's start with the no solution case. I'm going to tell you right now, this matrix is, it represents a system of a 3x3 system that does not have a solution. So what I want you to do is I want you to maybe pause the video and try to row reduce the thing, and I'm going to row reduce it myself, and I'll just put up the reduced echelon form kind of next to it, and you can check your work against mine. Right, so there it is. I've row reduced it. I got this, and really the big issue is this right here, this row of all zeros and then a 1 on the far right. Now what this is saying is that 0x1 plus 0x2 plus 0x3 is equal to 1. If you think about it, no matter what x1, x2, x3 are, if I take all of them, I multiply them by 0, and I add them together, this is like saying 0 equals 1. So if we see that, we know that we have a no solution scenario. All right, now the last example I've got for you in this video is the infinitely many solutions case. And again, I want you to row reduce this thing on your own and then check your work against mine. So in like 5-10 seconds, my fully reduced matrix is just going to pop up on the screen. Okay, there it is. So we've row reduced the thing, and we see a row of all. And now that doesn't always mean infinitely many solutions. If we were to see a row of all zeros and then above it a row of all zeros and then a 1 on the right side, that still means no solution. Okay, but at this point we're seeing otherwise just a row of zeros and then other stuff in not a row of all zeros and then a non-zero. Okay, so we're going to have to do some work to interpret this. So the first thing you want to do is you want to go over here to the non-zero rows and kind of like unpackage what are they saying. So we're saying x1, that's not very good, we're going to say that x1 plus 0 minus 5x3 equals -3, and x2 plus 1x3 is equal to 1. Okay. What you're going to do is you're going to kind of take, but what I recommend doing is, the variables that those leading ones represent, right? They're right there. Just solve for those in terms of the other one or other ones, and those will be the free variables, the ones you solve in terms of. So I'm going to solve for x1 and x2. I've got x1, whoops, it's supposed to be in gray. I've got x1 equaling 5x3 minus 3. x2 equaling 1 minus x3. And then x3 seems like it can be whatever it wants. Okay, so this is, kind of an algebraic specification of the solution space, but I think we can do a little bit better because of the work that we've done so far this year. I'm going to say that this looks like 5t minus 3, 1 minus t, and t. And we've seen something like this before. This is the equation for a line in space. But if you think about, these are 3 planes that are intersecting in a way that has infinitely many solutions and 1 free variable, that probably means that the 3 planes are intersecting in a line. And we'll see more evidence of that later on in the course. So this is the set of all solutions to this system. Now, to wrap, I think I didn't mention this, and I think I'm going to talk about this more at length in the next video. But if we can, the coefficient matrix here, if we call that A, and we say that our solution is a vector x, and I kind of already wrote that on the one that had a unique solution. So A is the coefficient matrix that we defined at the very beginning. X is, in this case, x1, x2, x3, right? But it's like kind of the solution that we're looking for, equals, and we call this thing here vector B, okay, that our system of linear equations is equivalent to the matrix equation AX equals B. And, our solution set is going to be X is equal to some kind of vector like this, with T being some real number. And we know from, the few things we've done so far in the course that that thing in gray, that vector equation here, this is going to, the image of that is going to be a line. And I think at this point, you need to just practice your row operations yourself. We will go to higher dimension matrices than 3x3 systems, but you can watch me do this all day, but there's nothing quite that can quite substitute for you doing it yourself. So happy row reduction.